All right. Whoops. Wrong color. We're going to look at what we call trees. That's a graph theory term. My class this morning thought this section was actually pretty easy, so hopefully you guys are the same boat. If you kind of understood the sections before this, I think this section will be actually quite easy. All right. So the first thing is I'm going to do, since we're talking about a tree, this is not a literal tree, it's a tree in graph theory. We're going to define what a tree is in graph theory. Okay. So a tree is a graph that has no circuits and is connected. Okay, that's a tree. Okay, it has the following properties. Some properties of this, of every tree, okay, will be one, there is one and only one path joining any two vertices. Okay, so that's pretty self-explanatory. That means that if I have my tree is drawn, my graph, which is a tree, is drawn, then if I wanted to, join, say, A and E with a path, there was an A and E vertice, there would only be one way to get there. There couldn't be two different paths. Okay. Two, every edge is a bridge. That's a big one right there. Okay, what that basically means, guys, is that if you pull out any edge, it disconnects the graph right away. Because remember, a bridge is any edge that when I pull it out, it disconnects the graph. Okay. So seems kind of archaic here. Let's do some little examples. Okay. So if I do this, if this is my graph, okay, I guess the question I have is that a tree based upon the definition I just gave? Because remember that a tree has to be connected and it has to have no circuits. And the answer is what? Is it a tree?
No.
Not a tree. Why?
No, it's not connected.
Right. It's just good. Okay. So now how about this one? Do another one. How about that one?
That's a tree.
Is that a tree? Who thinks it's a tree?
I do.
Okay. Todd thinks no. Why is it not a tree? Why do you think it's not a tree, Todd?
I was just gonna say that everything isn't connected still. Like vertices B and E and D aren't connected.
Oh, that's true. Yeah.
Well, they are connected. They're just
Okay.
not a complete graph though, right, Andre? So like, doesn't have to be a complete graph would mean that B would have to be connected to everything else. A connected graph just means I can get from any point to any other point with a path. So I can get from B to E with a path. So this is still a connected graph. It doesn't have any breaks in it.
Okay.
Right. So what Todd said is actually correct. Not all of them are a bridge. But even simpler, think of it simpler than that. This is not a tree. Hang on. And the reason it's not a tree is because it has a circuit. What's a circuit? A circuit is when I can start at 1 and make a path that brings me back to it. Isn't that a circuit I just drew right there? With the green? Okay.
Yes, with the green.
That's not supposed to be a precursor to Christmas, just so everybody knows. Anyway, this has a circuit in it, because remember, a tree, reminder, just a quick
There's no circuits.
yeah, no circuits. Reminder, a tree is connected and no circuits. Okay. A tree is connected with no circuits. Well, the first one is disconnected and the second one has a circuit, so neither of those are trees. Okay, so now let's look at something that is a tree.
Yeah, with some circuits.
So here's a simple one. There we go. A, B, C, D, and E. Okay. Is that, that looks like it's connected, doesn't it? I can get from any letter to any other letter with a path, can't I? Any vertice to the any other with a path. So that sucker is connected. Are there any circuits? Meaning if I start at B, A, E, D, or C, can I get back to it with a path? No, I cannot. Because look, as soon as I go here, I can't go back over the same thing I've already done,
Can't
right?
retrace.
Same with all of them.
Okay.
Can't retrace, right, for a path. So this is a tree. This is a tree. Okay. So now we're going to build some theory here. Okay, we're going to build some theory. So you know what a tree is and what's not a tree. The big idea is that it has to be connected and it has to have no circuits available, which means everything is a bridge. So you could use Todd's reasoning a little bit ago. Okay, so let's do another one here. All right. So a subgraph. We're going to talk about a subgraph. Whoops, I want to erase the example. It's not an example. A subgraph of an original graph is any set of edges and vertices chosen from the original graph. Okay, that's it. A subgraph of an original graph is any set of edges and vertices chosen from the original graph. So let's take an example here. Here's a graph. We're going to do one of our most basic graphs that we work with, which is the square with the diagonals through the middle. Okay. So here's A, B, C, D. Okay, that's a graph. Let's draw a subgraph. Here's my subgraph. There we go. Just made a subgraph. So it's just, I just picked some random vertices. I kept all 4 vertices, but I didn't keep all the edges. Okay, that's a subgraph. Okay, very, very simple. Okay, now we need that term subgraph so we can talk about something called a spanning tree. Sounds scary, doesn't it? It's actually not that scary once you understand it from an example. All right. A subgraph that contains, all the vertices of an original graph okay, contains all the vertices of an original graph, is connected and contains no circuits, is called a spanning tree for the original graph. That sounds pretty scary, but it's really, let me explain why it's not so scary. Okay, this is the spanning tree. A subgraph that contains all the vertices of an original graph, is connected and contains no circuits, is called a spanning tree. So basically, here's the idea, guys. If I give you a graph, let's take this one for example. I'm going to make a big old graph here. Okay, A, B, C, D, E, F, G, H. Okay, got this big old messy graph. Okay, so that is a graph. Now that graph is not a tree because it has a lot of circuits in it, right? I mean, I can go for, so for example, one circuit is I could just go around like that. There's a circuit starting at C and ending at C. So this is not a tree. But if I want to find a spanning tree for this graph, what I need to do is I need to find a subgraph of this graph that hits all the vertices A, B, C, D, E, F, G, and H, but is a tree, meaning it doesn't have any circuits and it is connected still. So for example, I could do something like this. If I traced it out in green, I could go that one, this one, that one, this one, that one, maybe here and down there. And you can see now that if I draw that, okay, it's not perfect as far as the scale, but you can get the idea here. You can kind of see A, B, C, D, E, F, G, H. That's a spanning tree. You can see that it's a spanning tree because it meets the criteria of what I just said above, which is it's a subgraph, right? It is definitely a subgraph. I grabbed edges and vertices from the original graph. It is connected. I can get from any letter in this graph to any other letter with a path. And it does contain no circuits. I can't go start at any point and get back to it. So this is called a spanning tree of the original graph. It's not the only one, by the way. There's a lot of different ones I could do. There's a lot of ones that are unique. So I could also, for example, if I picked a different color, say blue, I could do one that goes maybe here, goes there, and then just kind of shoots into the insides here and stops. Now I've hit, in the blue, I've hit all 4 of them as well, all 8 of the points, the vertices, and that is not connected. It is connected rather, but it is not, there's no circuits because there's dead ends here on the ends here in the corners, the C, D, E, and F corners. So there's more than one spanning tree for a given graph, okay? There's more than one spanning tree. Okay, but this first one in green is the one that I will look at here for a minute. So let's try another one. Let's try another one here. So I'm going to give you guys one to do. Okay. So here's a spanning tree. I'm going to do this and that. We're going to put a bunch of stuff here. Okay. So this is A, B, C, D, E, and F. Okay. So what I want you guys to do is I want you to try to find a subgraph of this graph that is a tree. So it's got to hit all the vertices, A, B, C, D, E, and F. Doesn't have to hit all the edges, obviously. And you want it to be a tree in the end. And it's got to span the whole thing, which means spanning means it has to hit all the vertices. So take a second and try that. All right, Todd, I actually agree with that. I think I do. So I'm going to do this here. So if I want to do my spanning tree here, I think you're saying to do this. Do that, then go to C, then go to D, then go to E, then go to F. Is that what you're thinking? That is a way to do it. That does hit every vertice. It is definitely a spanning tree. Okay. It is definitely a spanning tree. Okay, there's a lot of different ways to do this, guys. That's a way to do it. You can look at, go ahead.
So I kind of scribbled it out. If you can kind of see it, I can try and redraw
Let me
it.
see it.
Didn't think this one right here. I didn't think it would work because I started at B and went all the way around it and it went to A. That's not a circuit though, right?
Let me take a look here. So that one, that is still okay because I can't get back.
To B, where I started.
Well, it looks like, right, that is actually okay because you can't get back it. You can't get back to B and C and D and H and all of them. None of them you can get back to, correct, if you
Okay.
started. So that is a valid one right there.
Okay.
That's valid. Yep. So hers was this one. Melody's was this one where she went, I think she went bam. I don't have it remembered, but didn't you go like this basically? Right?
Yeah.
That's okay because if you take a look, it might appear that there's circuits in there, guys, but you got to be a little bit careful. There are not circuits because A, B, C, D, E, and F. There actually are no circuits because you might be led to believe that like maybe this is a circuit or something like that. But it's not. Why not? Because this isn't a spot you can turn, is it? That's not a vertice, even though it looks like it might be because they intersect. So you can't actually get, if I start at D, let's make sure I can't get back to D, can I? Right? There's no way to get back. So that actually is a tree as well. There's a lot of different trees that you could create, guys. There's not just one answer for most of these. There's not just one answer for most of these. Any questions so far on how we find a spanning tree? We're trying to find a path basically through the graph or a subgraph of the graph that is connected and has no circuits. All right, that's a good one. So now, one of the things we're going to try to do is we're going to try to find a minimum spanning tree. And this is where the mathematics becomes actually useful for applications. Kind of like the traveling salesman problem. The minimum spanning tree. What is the minimum spanning tree? It's the weighted graph. Sorry, my bad. It's the spanning tree for a weighted graph. So we're going back to weighted graphs, which are the graphs that have the numbers on the edges. Spanning tree for a weighted graph with the smallest possible weight. Total weight. All right, that's a spanning tree. Okay. So we want to, this is basically, hey, how can I connect all these cities with the smallest amount of travel time? Similar idea, similar idea. Okay, and we're going to use an algorithm to do this one called Kruskal's algorithm. We got a lot of algorithms in this section. Kruskal's algorithm. So let's look at Kruskal's algorithm. Okay, so this is to find the minimum spanning tree for a weighted graph. Okay, well, so we first find the smallest weight edge and mark it red. Okay, so find the smallest weight edge and mark it red. Okay, and if there's a tie, if it's a tie, choose randomly. So let's say there's two edges that have the same number, like they both have a 13 on them. Just choose one of them randomly, doesn't matter. Okay, 2, keep choosing the next smallest weighted edge until all vertices are hit, avoiding creating a circuit. Okay, because we can't create a circuit, can we? And you're done. So that's a very simple algorithm. Very, very simple algorithm. So let's do one. So I'm going to create a little one here, just a small little one here. Okay, so this is 35, this is 24, this one's 20, this one's 8, this little guy's 15, 12, 17. Okay, so what we want to do is we want to pick the smallest edge first. Okay, so it looks like the smallest edge is 8. Okay, so I'm going to put a little 8 over here just to add these up. The next smallest looks like it's 12. Okay, so I got a 12. Next smallest is 15. 15. Next smallest is 17. We haven't hit every vertex yet, and we're still haven't created any circuits, so we're okay so far. And then the next smallest looks like it's 20. Still haven't created any circuits. So the next smallest should be 24, wouldn't it? And why do I not want to pick 24? What's going to happen if I pick that 24 right there, that edge?
You make a circuit.
I'd make a circuit, right? Because if I go here, I've now got a circuit right there. You see that? So I don't want to pick that one. So that means I skip that one. So what I would do is I'd stick an X through that so I know I'm not going to use it. And then my last one I'm going to pick, because I still haven't hit this vertex yet, right, is the 35. So what is that total weight? I'm going to add those up quickly. So that yellow is my tree. The yellow drawing is my tree. And then if I add these up, I get 8 plus 12 plus 15 plus 17 plus 20 plus 35. It's 107. That's my total weight of the whole graph. That's pretty easy procedure, isn't it? I think it is. Okay, let's try another one. You guys try one here. It would take me a minute to draw it. These are a pain to draw. Okay. So I've got a B here, go up to C, go over to E, go down here, go over there, go over there. Okay. And then I've got a D here. So this, that, this, that. It's here. This there. Okay. So I'm going to put a bunch of distances in here. 259, 262, 256, 242, 264. This one's 251. This one's 253. This one's 245. $249. 253 up here. 251 over there. 274 down here. Okay. So what I want you to do now, I'm going to erase that one's poorly written. I want you to find the tree, minimal spanning tree, using Kruskal's algorithm, and we'll come back and I want you to add up all the numbers like I did in the last one and see if we all get the same answer, and go ahead and report your answer in the comments of your addition. Okay, so let's use the algorithm. So Kruskal's algorithm says we're just going to start with smallest one. So what's the smallest one here? It looks like it is 242, right? That's my first one. So 242. What's the next smallest one? 245 over here. So that's 245. Is there there's a 249. I think that's next, isn't it? There's only one 249. There's a couple ties in here. So 249. So far we haven't hit any circuits, right? Haven't hit any circuits, and we haven't hit every vertex. We've got to keep going. Okay. And then after 249, I think 251 is the choice. But look, we have two of those, don't we? We got this one and that one. Which one do I choose and why? Well,
Can't you do it just random?
yes, I would do it random, but in this case, I can't do this one because you see I'd make a circuit. See that?
Mm-hmm.
So generally you could do random, but in this case, no. Yes, you do random, but you got to make sure that you're not making a circuit. So I can't choose that one, which means I have to choose the other one. So I'm going to cross that one out right here because we know just to know we're not going to use it because it makes a circuit. So now that I'm at 251, I can do 253 is the next biggest one, isn't it? Well, 253, I got two choices, this one or that one. Those two I could choose randomly, couldn't I? Doesn't matter. I like the one on the outside better. I'm not sure why. So I'm going to choose that one. So I forgot to add the 251 here, and then the 253 now. Okay, now what's next? Well, 256 would be the next biggest, wouldn't it? But I can't choose that one. Why wouldn't I choose the 256? Doesn't that make me a circuit now? This circuit right there.
Mm-hmm.
So I don't want to do 256. So it looks like my only other choice now is 259, isn't it? Next choice. I'm done. Why am I done? Have I hit every vertex? Yes, I have.
Yeah, you did. Yep.
I did, and I have a tree, don't I? Definitely have a tree there. There's no, it's connected. If you look at the red, it's definitely connected. And I forgot to cross this out, by the way. We didn't use that one. And it is connected, and there's no circuits. So let's add those up now for a minute here. 242 plus 245 plus 249 plus 251 plus 253 plus 259. It looks like it's $14.99 is what I get. That is correct. Does that make sense? So that's my minimal spanning tree using the Kruskal's algorithm. So guys, it's really simple. Pick the smallest one. If there's a tie, pick randomly and avoid circuits. That's it. And keep going till you hit every vertex. So it's kind of similar to the. So in this chapter, guys, there's a lot of different, procedures to remember, right? We've got the Kruskal's algorithm. We've got the Euler method. We've got the method from the weighted graphs from the last section. So we've got a lot of little methods. The nearest neighbor method, do you remember that? The brute force method. If we're looking to find an Euler circuit or an Euler path, we've got Fleury's algorithm. Okay, so we've got a lot of different algorithms you got to keep straight, and they all have a different purpose. And we're going to look at those. I'm going to summarize those here in a few minutes and just go over those again. I made a circuit, didn't think anything of it at first. Well, that's fine. You could probably make a circuit, and that's probably how you got a higher number, but you got to make sure you're making the minimal one. You got to follow the Kruskal's algorithm. Okay, does that make sense? Okay, well, I'm going to delete that. And so what I'm going to do is we're going to review all these different algorithms, guys, and we're going to talk about when we use them. So let's look at the different algorithms we've learned in this chapter, because I think one of them is Fleury's algorithm. Okay, does anyone know why we use Fleury's algorithm or what we're using it for? This is to find a what?
Euler path or circuit.
Correct. Okay, so if they're asking you to find an Euler path or circuit, you're going to use Fleury's algorithm. Okay, what if I'm using the brute force or nearest neighbor? Both of these are trying to find the same thing. What are we trying to find there? We're trying to find Hamilton circuit, aren't we?
For both?
Yep. We're trying to find a Hamilton circuit of least travel in a weighted graph. Remember, this is the traveling salesperson problem. Okay. So So a Hamilton circuit means we hit every city and we do it as fast as we can. So remember, this is the optimal. We're trying to find an optimal path. Okay, so that's the brute force the nearest neighbor. And then what's Kruskal's for?
That's
We're
find
trying
the
to
smallest weight.
No, this is we're trying to find a minimal spanning tree on a weighted graph again. Okay, so it's really important to understand these different things. Okay, next class, I'm going to spend some time reviewing a little bit more. I'm going to review what the Euler's theorem says. We'll review all the definitions of what a Hamilton circuit is, a Hamilton path, an Euler circuit, an Euler path. We'll review the definitions of a tree again. We'll look at Euler's theorem, which is way back from 14.2. We'll look at the definition of connected and disconnected again. We're going to just do a big review of all the definitions. I'm going to do a lecture where we actually review all the definitions, all the algorithms, do a couple examples, and then we'll go ahead and answer questions that you guys have. Okay?
Sounds good.
So now we're going to do one more. I want to do one more problem with Kruskal's algorithm. Okay? One more problem with Kruskal's algorithm. Just to make sure we got it down. Okay? Here it is. Draw my graph here. Okay, this is 11, 17, 10, 12, 9. The one all the way across is 15. This one going diagonal is 18. This one going diagonal is 14. Okay, so let's practice how to do this one. All right, so what would I choose first? What would I choose first? What's the smallest
9.
one? All right, choose 9. What's next? 10. Right? Next would be 11.
11.
Then would be 12. Am I done?
Yeah.
Yep.
I've hit everything, haven't I? So you know you're done when you've hit every vertex, and you don't, and that is definitely a spanning tree, isn't it? Doesn't it hit every vertex? And it is connected, and there are no loops, or what do you call them? Circuits. There are no,
Circuits.
yeah, my bad. I'm losing track of reality here with all this COVID, right? So 9 plus 10 plus 11 plus 12 is 42. So 42 is the total weight of that tree. So that's it, guys. That is it for 14.4. So now you've got roughly 2 hours to work on that chapter 14 review. That will be due Saturday. Okay, so I would start work. I would just stay right now. I just open it up right now and start working on that chapter 14 review. If you should have the 11 review done. The 12 review is due Wednesday. I'm letting the 14 review be due Saturday, just because then you get some extra time on it. But do as much of it as you can between now and Wednesday, so that you guys have some intelligent questions to ask me on Wednesday. Okay. So the rest of this class is designed to be doing the review. So that's all there is for new material. Any questions?